Hello students, welcome to today's session of thermochemistry. Today we will do the theory part. The most important thing I want to make you remember is that in whole of the physical chemistry, the theory is not that much important. Yes, I'm not saying it is not important, but from a student point of view, or from many of you have heard also that in physical chemistry, the main thing is solving numericals, right? And getting the formulas right. But this chapter is an exception because you need to get the theory very correctly, right? Because its definitions are very important to know the formulas. If you are not aware about the definition accurately with whole accuracy, then you can't know the formula and you can't solve a numerical. So with this point in your mind, let us start the chapter. So the first thing is we will study about the thermochemical standard state, that what is the thermochemical standard state. Then the first important thing, enthalpy of reaction. Okay, the enthalpy of reaction is basically the enthalpy change during a reaction. We have it is very clear from the statement only, from the terminology only. And what we will do in this whole chapter, we'll discuss its type. So this is the first important thing. So before that, we will see that what are the factors that affect it, and then we'll see the type. There will be various types, and you should be aware about each of those. And then only it will be then and then it will be possible to solve the numericals. Clear? Then second thing we will see, which is the most important one. So first is this enthalpy of reaction. Second thing is the Hess's law of constant heat summation. So it is basically a very powerful tool through which you can know the enthalpy of a reaction if you are having some information in the background. Okay. Moving on to further, so this is another type of bond enthalpy or bond energy, which is nothing but the enthalpy of a tool used in the enthalpy of reaction. Then we have calorimetry. So this is a theoretical thing to calculate the enthalpy change, and this is a practical applicability of this, say here CV, which is heat at constant volume. Okay, so that thing is being utilized here in the calorimeter to calculate the enthalpy change. So same thing is written that at constant volume the calorimetry is called as the bomb calorimeter. At last we will sum up with a summary. So let us start our today's class. Disclaimer: the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of the images. If you are the owner of any of the images used in this deck, have any concerns or issues, please contact us at sathee@itk.ac.in and we shall remove the images. First thing, the basic definition of thermochemistry. Okay, so we will slowly move to this thermochemical standard state. First we will get to know what is thermochemistry, then we will move there. Okay, so thermochemistry is basically a branch of thermodynamics which deals with the chemical reaction and the physical reaction. So you know that thermodynamics deals with the exchange of heat. Okay, but thermochemistry specifically deals with the exchange of heat in a reaction. Okay, so thermodynamics includes the pressure volume work also, but in thermochemistry it does not include that thing. It only includes the physical and chemical reaction both. Clear? So you know very well that whenever a reaction takes place, a lot of heat exchange take place, like in the minute level. So whether it is a physical reaction or a chemical reaction, there's always an exchange of heat. So we will look upon this, and our main focus will be on the system, right? Because obviously we are interested in the system. That is the reason we are doing it. We are taking that system. So our main focus will be on the system. In some cases we focus on the surrounding. That is a very difficult thing to do because surrounding is very complicated and very large to say analyze. Now all these changes are, means in the system, is calculated with the help, is in the practical life it is calculated with the help of calorimeter, and I have told you this in the start only. So chemical reactions is exchanging heat. So this exchange of heat can be in two ways. Okay, so those two ways are used to classify the reactions in two types, which are exothermic reactions and your endothermic reaction. Clear? Now, what are exothermic reactions? So, exothermic reactions are those in which the heat is transferred to the surrounding, right? Means the system is rejecting the heat and the surrounding is accepting the heat. Clear? So, a very obvious example would be this, which is burn combustion. So, here we have taken the combustion of aluminium. So, most of the combustion reaction that you will see in your day-to-day life are exothermic. They produce heat. So the combustion of aluminium is exothermic, and how we can identify it? So with the help of this enthalpy of reaction, which is saying that it is having a negative sign. Negative sign means the system is losing that heat, right? So for that reason, that overall reaction is exothermic. Now the opposite of that would be endothermic, in which the system takes up the heat from the surrounding, and for that we have taken the example of N2O2 giving us NO2, okay, 2 moles of NO. Here what we have seen, that it has a negative sign. Here we have a positive sign, means the system is taking the heat, which is 90.4 kilojoule. So now let us try to define the thermochemical standard state. So till now it must be clear to you that knowing this thermodynamic exchange in the chemical reaction is very, very important. So it is important from for everyone, right? So in the whole world, the reactions are being set up by the researchers, and the data is being collected and published as the research papers. So to access that data to someone else, or to convey the data to someone else, it should be more and more convenient to be get studied. So to make it convenient, what we have done is we have kept or done all the reaction at some standard state, means almost all the reactions. There are reactions which requires specific conditions, and for those the standard conditions are not applicable. So to keep the convenience of research throughout the world, we have taken the standard state. And what is that standard state? So that standard state is the state of a system or a substance, if you're talking about substance, in which it is most stable. So that state which is most stable at 1 atm pressure and 298 Kelvin. Clear? So again I am repeating it. What is the thermochemical standard state of a substance? So it is basically that stable state which is taken at 1 atm pressure and 298 Kelvin. Now under this condition, any parameter is designated using 0 or not. So 0 or O, sorry, 0 or O. So you must have seen written that del H not, right, or del U not. So this not or 0 is representing that, or the calculation or the value that is being given here is nothing but your standard value. Clear? So the purest form of liquids and solids, most stable states are considered with 1 bar pressure and 298 Kelvin. So what is being written here, that if you are taking a solid or a liquid, then for that you take the pressure as 1 bar and keep the temperature as 298 Kelvin. Whereas if you are taking gas, so suppose you are taking gas, then for that what you do, you keep the pressure 1 atm, and if you are taking a mixture of gases, then you keep the composition or the individual contribution of each gas to be at 1 atm pressure. Further, if you talk about the solution, then in that case we keep the concentration of solution as 1 molar. Okay, so these are the way we can take the standard state for different type of say substances like your solid, liquid, gas, or solution. Clear? Now moving on to the enthalpy of reaction. So what is the standard enthalpy of reaction? So it is basically the heat or the absorbed or evolved, both things, right? It is the heat that is absorbed or evolved during a reaction. Now why are we telling it as heat or enthalpy? Because most of the reactions that we do in our research laboratories on our day-to-day life, the reactions we observed are mostly occurring at a constant pressure. Clear? And the heat that is being exchanged at constant pressure is what it is called enthalpy of reaction. Clear? So again I am repeating it, that most of the reactions that you do, okay, most of the reactions that you do, you are doing it at constant volume, and since you are doing it at constant volume, therefore the heat exchange would be equal to the enthalpy change, which is QP. Okay, QP will be equals to del H, and it's very well known from the thermodynamics. Now we are taking a R here. Now you can put this R here also, there is no issue in it. Both ways are correct to represent it. Clear? So for example, This is an example of a thermochemical equation. So this thing is also, this terminology is also important, which is called thermochemical equation. So thermochemical equation is basically a balanced chemical equation with its state mentioned very correctly, and at the same time the enthalpy related to that reaction should also be mentioned. Like here, in this case, it is mentioned as minus 890.3 kilojoule. So it is basically the nothing but a combustion of methane to give carbon dioxide and water. So how can we know the enthalpy of reaction? So it is basically the sum of enthalpies of product minus the sum of enthalpies of reactant. Okay. Now mathematically this can be written in this way: summation of H of products, which is enthalpy of products, minus summation of enthalpy of reactant. Now a very important formula going to be displayed, which is this one. So this is a very important formula from thermochemistry point of view, because it is relating your formation with the reaction. You will further know that why it is important, because when you will solve numericals, then you will see this formation used multiple times, right? Now I am not defining what is standard enthalpy of formation, which is represented here with delta HF naught, but just keep this formula in mind, that you can represent the enthalpy of reaction using the standard enthalpy of formation of product minus the standard enthalpy of formation of reactant. Just take the summation and you will get the point. Clear? Now again, the standard enthalpy is being defined here. So I have already told that if you are keeping the conditions for the state as standard, that is 1 atm pressure and 298 Kelvin, then all the functions that are measured will be considered as standard standard values, right? So like here we have standard enthalpy, which is basically the enthalpy of a reaction or the enthalpy change during a reaction occurring at standard condition, that is 1 atm pressure at 298 Kelvin. Okay, so we have taken a not sign here to denote the standard condition and a R sign to denote that it is a standard enthalpy of reaction. Now there are three cases. First case is that if your product enthalpy is equals to the reactant enthalpy, that is we are considering this one. So if you consider this equation, that according to this equation your delta RH or delta H will be 0. Next thing, if your product is having more enthalpy, then your delta H will be positive, and if your reactant is having more enthalpy, then your delta H will be negative or exothermic reaction. Clear? So this is the basic idea of the enthalpy of reaction. Now we will see what are the factors affecting the enthalpy of reaction. So first is physical state. Okay. Second is the allotropic form, means which allotropic form we are dealing with. Suppose we are taking carbon, then it is whether graphite or it is whether say graphite or carbon. Okay, so you must be or coal, right? So you must be aware about it, that which elemental form or which allotropic form you are dealing with, because for everyone you will have a different enthalpy value. Then chemical composition states of products and reactants, amount of reactant, obviously temperature and reaction conditions, that what is the temperature, what is the pressure, and what is the volume and all. Temperature is already mentioned, so pressure and volume and number of moles, so each of these things are important. Clear? Now we will see what is the type of enthalpy of reaction. Now just keep your mind intact, because now you will see various types of enthalpy of reaction with various definitions, so you should be aware about these definitions accurately, starting from standard enthalpy of formation, the most important one, which is basically the enthalpy change when you make the substance for whose standard enthalpy of formation you are looking for from its elements in their most stable state or the standard state, which I have already defined. So it is being written here also that standard enthalpy of a change of a formation is what? It is the enthalpy change when the 1 mole of that substance. Now this is also very very important. The question may be asked in your exam, that out of the given thermochemical equation, which is the standard enthalpy of formation, then you should remember that 1 mole of the compound should be formed at last, and it should be formed from the most stable state or the aggregation in the standard state. So we have already studied what is aggregation standard state earlier, right now. Okay, so it is the most stable state at 298 Kelvin, 1 atm pressure of the given element for which we are looking for. Suppose we are forming methane. So methane is what? It is containing carbon and hydrogen. So what we will do, we will take the most stable state of carbon, which is graphite. So you must remember this, that the most stable state of carbon is graphite, and for hydrogen the most stable state is gaseous. So just if you want the standard state, just go back to the NCRT. You will find the table there which dictates the standard state for each of the element that you are dealing with. Now you will find that to do this transformation, delta HF naught is found to be minus 74.8 kilojoule per mole. Clear? Next is a very important point, that if you are considering the standard enthalpy of formation for standard means elements at the standard state, then it will be always zero. For example, if you consider the standard enthalpy of formation for C graphite, then it will be zero because carbon is in more stable state at 298 Kelvin and 1 atm pressure. Similarly, if you are considering the enthalpy of formation for H2, then it will be also zero. So basically, what I want to say is that if you take an element and if you take its most stable state at the standard condition or the standard state, then in that condition the enthalpy of formation will be always zero. Clear? It will be always zero. So from here, if you are knowing the standard enthalpy of formation for this and this, then what you can do, you can calculate the enthalpy of reaction. So in this case, your enthalpy of reaction is equal to the standard enthalpy of formation of methane, because for this and this are zeros as there is standard state. Clear? Now this formula is I have already to make you see. So you should remember that what is the standard enthalpy of any reaction. So it can be written in terms of products and reactant, that it is the enthalpy of reaction formation of product minus the enthalpy of formation of reactant. Okay, clear to you? Now moving further. Now what is delta HF naught? So it is enthalpy of formation of product, and delta HF naught R is the standard enthalpy of formation of the reactant. Clear? The next type, the first type is the standard enthalpy of formation. The next type is the standard enthalpy of combustion. So what is standard enthalpy of combustion? So it is basically the enthalpy change when 1 mole of a substance undergo combustion under at excess oxygen supply. So it is written here also that if you are combusting something in the standard state, okay, and if you are taking 1 mole of that substance, not in the standard state, you are combusting something and you are combusting 1 mole of that, then the enthalpy change regarding that reaction will be enthalpy of combustion. Clear? Okay, so again I would say that the most important point would be that you should remember that we are combusting 1 mole, and similarly during formation we are forming 1 mole there. So this is an example which is combustion of methane. We have seen this example earlier also. So it is basically the reaction of methane with oxygen to give CO2 and H2O, and the amount of heat that is released is 192 kilocalorie per mole. Now you must have seen that most of the combustion that goes around you, it gives us heat. Okay, means that those combustions are what? Exothermic reactions. But it is not always the case. There are certain reactions in which your heat is not given, and in that case your enthalpy of reaction is positive. For example, we have N2 plus O2 giving us 2NO, which is having a delta H positive. Similarly, the oxidation of fluorine is also, or the combustion of fluorine is also a positive enthalpy, is having a positive enthalpy value. Clear? So remember this, that if you are forming N2 and O2 and NO, or if you are forming OF2, then the standard enthalpy, then the combustion will be always positive, and other than that you will always take the enthalpy of combustion as negative. Next we have enthalpy of neutralization. So it is very clear from the terminology also that we are talking about the neutralization. So whose neutralization? So it is the neutralization of 1 gram equivalent of an acid by 1 gram equivalent of a base. Okay, so it is that enthalpy change, and it is represented by delta HN, where you should remember that its value is always fixed for strong acid and strong base. So if you are neutralizing a strong acid with a strong base, or strong base with a strong acid, then in that case its value is always fixed. So let us see what is this value. So this value is minus 57.27 kilojoule per mole, or minus 13.7 kilocalorie per mole. So these are the values for the for the neutralization of a monobasic acid, strong acid, and a monobasic strong base. Clear? Okay. Next is, this is an example here. So how can we know it? So see, this will break into ions. So if you cancel out this ion, this ion, this anion, then what you will simply get? You will simply get the formation of say water, which is always fixed and is equals to minus 57.3 kilojoule per mole. Clear to all of you? Now, why we are saying that we should keep strong acid and strong base? The difficulty is that with the weak base that uh, apart from the formation of water, there is also energy that is required for what? For the breaking off or for the dissociation of weak acid. Clear? Okay. So why is it so? Because for a weak acid, the complete dissociation is not applicable and it depends upon temperature. So whenever you do a whenever you do a neutralizer reaction, heat is released and that heat is being absorbed by the acetic acid to get dissociated. Clear? And to get dissociated, since some amount of heat is being taken, therefore what will happen? Therefore your neutralization energy will go down by some value. Is it clear to all of you that what is the meaning of this? So you should remember that for a strong acid and strong base, its value is fixed, whereas for a weak acid and weak base, it is not fixed because some amount of energy is being used to dissociate that particle. Okay, clear? Now the absolute value of HF is more than 57.3 kilojoule. This is due to the very high heat of hydration of fluoride ion. Okay, because most of the fluorine ion is being hydrogenated and that releases energy. So it is more than this 57.3 kilojoule per mole value. Okay. Now moving on further. Now we'll talk about standard enthalpy of atomization. So what is standard enthalpy of atomization? So it is basically the conversion of your compound into gaseous atoms, right? So suppose you are taking X2 molecule, then you will convert this into 2 moles of X gaseous, and the enthalpy change during this whole process is called as standard enthalpy of atomization. Now next is lattice enthalpy. Now what is lattice enthalpy? It is the amount of heat that is required to break a given lattice into its constituent ion, which should also be present in the gaseous state. Clear? So it's same thing written, that is the enthalpy change when 1 mole of a ionic substance dissociates its ions to get the gaseous atoms. Clear? Okay. Now this is an example for you that we are taking 1 mole of NaCl and completely dissociating into Na plus and gaseous minus. Next we have standard enthalpy of hydration. So what is standard enthalpy of hydration? So standard enthalpy of hydration is basically the addition of water of crystallization. So you will get it with the help of the equation. So as I've already written you, so it is addition of specific hydrate of water to the given compound. So this is the example. You must have seen this thing, which is CuSO4 or 5H2O. It is basically formed by the reaction of copper sulfate with 5H2O, in which the water gets coordinated to copper, and the delta H hydration will be minus 78.21 kilojoule per mole. So why it is negative? Why not positive? Because this is stabilizing the CuSO4 in the this is stabilizing the CuSO4 in the non-ionic state, right? Clear? So basically what it does, it combines with this ionic part of water and stabilizes the positive or negative addendum accordingly from where it is attached. So what happens during a dissolution? During a dissolution, the state of a system changes, while during dehydration, there is no change in the physical state of compound. So we'll see it later. Next, we have standard enthalpy of solution. So it is the enthalpy change when a given solute is dissolved in a specified amount of solvent in the standard state. Okay, the thing should be in the standard state. So suppose we have delta H naught solution, it will be simply delta H naught lattice minus delta H naught hydration. Okay. So what are we saying? That during solution, we can get this solution by subtracting del H hydration from del H lattice. Clear? Okay. Further, what is integral energy? So when we are when 1 mole of a substance is dissolved to form the pure solvent, then we call it as what? Then we call it as desired equation or integral heat of solution. Clear? Next we have differential heat of equation. which is differential heat of solution when we are dissolving the solute into a large amount of solvent, such that further addition of the solute does not changes what? Does not changes the so further addition does not changes the enthalpy of reaction. Now, if the solubility of a substance is known at two different temperatures, then you can use the Fentoff equation easily to get the enthalpy of reaction. So this is your equation: log S2 by S1 delta H 2.303 R 1 by R T1 minus 1 by T2, where T2 is greater than T1. Okay, clear? And S1 and S2 are the solubility at T1 and T2 respectively. Same thing is written. Next, we have standard enthalpy of hydrogenation. So what is standard enthalpy of hydrogenation? So it is also very clear from the terminology, but you should remember that it is the amount of enthalpy change when 1 mole of a unsaturated 8 compound is completely hydrogenated. Means the water is added to this unsaturated compound. Clear? So you can add it to, suppose, butane, which is but-1,3-diene. Here you can add it water. Okay, so you can add it to ethene also. So the amount of enthalpy change that is accompanied to this reaction is called as the standard enthalpy of hydrogenation. Next, we have a standard enthalpy of dilution. So what is standard enthalpy of dilution? So it is basically when 1 mole of a substance is added to such a large extent solvent, so that the stage so that what happens, so that no heat is dissolved or absorbed on further addition. So do that thing. Clear? Next is standard enthalpy of transition. So it is basically the change of given element from one anaerobic form to another. Suppose, so one more thing, you're taking 1 mole of a substance, then it will be called as standard enthalpy of transition. If it is say converting from S rhombic to S clinic, okay, then the enthalpy for formation is minus 13.14 kilojoule. Clear? Okay. Further, next we have standard enthalpy of fusion. So it is basically the conversion of solid into liquid. Okay. So the enthalpy change accompanying the change of 1 mole of a solid to the liquid is called as the standard enthalpy of fusion, and it can be written as delta H naught of solid, which is delta H naught of fusion, negative of delta H naught of fusion. Why? Because fusion is what? It is the opposite of the solidification. So what we do to calculate solidification, we take a negative sign against it. Clear? Now next is standard enthalpy of what? Standard enthalpy of vaporization. So what is standard enthalpy of vaporization? When your liquid is converted into gaseous, then we call it as standard enthalpy of vaporization, and the heat that is being exchanged is called as the standard enthalpy of vaporization, which is represented by this. Okay. Now the opposite of that would be condensation, and that is represented by del H not. Okay, clear? Moving on further, we have standard enthalpy of summation. So it is the enthalpy change when 1 mole of a solid substance is directly converted into gaseous. So in that state, the enthalpy of reaction is called, or the enthalpy of summation is called standard enthalpy of summation. Clear? So according to the conditions, change in enthalpy when 1 mole of a solid substance is sublimates is called the standard enthalpy of sublimation in the standard state. Now we can divide this sublimation part into two. First is delta H naught of fusion, and second is delta H naught of vaporization. So if you are converting the solid directly into gas, what we do? First we vaporize it, and then we first we melt it and then we vaporize it. So it can be two ways. Either you heat it too high so that it directly gets converted into liquid, or what do? You take the delta H of fusion minus the delta H of condensation, and then you can add it all and get the delta H of sublimation. Okay, so this is a direct consequence of Hess's law of constant summation. Next, we have enthalpy of ionization. What is the value of this? So its definition says that it is the amount of enthalpy change when 1 mole of a covalent compound on dissolution is split into to produce ions in the solution in the standard state. Okay, standard state. So this is called as what? This is called as standard enthalpy of ionization, where you're breaking a given compound into ions. So this is an example. If you're taking acetic acid and you're converting into acetate and iron plus. So in this case, it is called as standard enthalpy of ionization. Next, the theoretical way to calculate the enthalpies and all is called as the Hess's law of constant summation. So what it says that this Hess's law says that if you are doing a chemical reaction, you can do it in multiple ways, and for each reaction, you will have the same enthalpy. And I have told you earlier, and this thing is used to determine the Hess's law. Clear? So suppose you are doing a reaction, you are going from A to B directly, or you can go from A to C to D and then to B. Then in that case, your enthalpy change delta H is equal to delta H1 is equal to delta H1, delta H is equal to delta H1 plus delta H2 plus delta H3. Clear? Because enthalpy is a state function. So this the in total internal heat change accompanying a chemical reaction is the same whether the reaction takes place in one step or multiple steps. Clear? So this is written in the form of equation also that delta is equal to delta H1 plus delta H2 plus delta H3. Next we have application of Hess's law. So it is used to calculate various enthalpy of reaction, which is enthalpy of formation, enthalpy of transition, then determination of bond energy, determination of resonance energy. And what is resonance energy? So it is basically the experienced heat of formation minus the calculated heat of formation. So we'll study more about it in the later classes. Now whenever you are doing a chemical reaction, then you break and make bond at the same time, and that enthalpy change is called as the what? Bond energy or the bond for deformation energy. Clear? Now bond energy is the amount of heat which is required to break or dissociate a bond into particular type present in one molecule of the compound. Okay, so it is basically the breaking of a covalent bond. Now bond energy is taken as the average of dissociation energy of same type of bond present in one molecule. Clear? Moving on further, since a chemical reaction involves the breaking of old bonds and the formation of new bonds, therefore the enthalpy of reaction is what? It's written in this way. So this is just opposite of the previous one, and opposite related to most of the one, because here we are taking log of S2 by S1, not S1 of S2, and then we are getting some of bond energy of reactant and some of bond energy of product. Clear to all of you? Okay, moving on further. Next we have bond energy or bond enthalpy. So a molecule contains two or more covalent bond, and when you are breaking this bond, then you call it as what? Then you call it as the energy related to that is called as bond dissociation energy. Clear? So let us see further. So suppose this bond dissociation energy for CH is bond dissociation energy by 3. Clear? So this is for one CH. Okay, this is for one CH and there are 3 more CH. So we take the average. Now based on chemical reaction, if bonds are negative and if bond formation occurs whereas the bond energy bond energy values are positive if bond dissociation occurs. So that is clear from the formula also that delta H for a reaction is delta H of reactants minus the delta H of product. Clear? Okay. So if bond formation occurs whereas the bond dissociation occurs, both are positive and bond dissociation energy is equal to this. Clear? Next we have factors affecting the bond enthalpy, in which you have size of atoms. Smaller the size of atom, difficult is to break the bond. Okay, and that will result in a higher bond enthalpy. So we have first fluorine, then we have chlorine, then before that we have bromine, iodine and iodine. Okay, so fluorine is 1, then chlorine is 1, then bromine is 1, and then iodine. Okay, clear? So it depends upon the size of atom. So you can see that the size is getting smaller in the opposite way, therefore the enthalpy is decreasing. Now bond enthalpy of fluorine is smaller than the chlorine. Why is it so? So although the size of the fluorine is smaller, but the bond dissociation of fluorine is what? Bond dissociation energy is less as compared to chlorine. Because what we see here is that we are breaking a FF bond, that is CL-Cl bond. Okay, we are making a FF bond and a CL-Cl bond, and we know it very clearly that FF bond are having what? Shorter radius due to which the interaction is more. Okay, whereas the C-cell bond is having a larger radius, and hence it has a smaller bond dissociation energy. Next is our electronegativity. So what is electronegativity? So it is the measure of tendency or to attract a shared pair of electrons. So same thing is written here. So if we are talking about FH, then bond enthalpy decreases, right? The bond enthalpy decreases because the electronegativity difference is also decreasing. Clear to you? Now next we have bond length. What is bond length? So it is basically the bond dissociation energy. It is basically the bond distance between the two nuclei. Okay, number of bonding electrons is what? Number of bonding electrons that are present in the bonds. Okay, so that are present in the bonds are called as the number of bonding orbitals. Clear? Then this is the equation: carbon triple bond carbon, carbon double bond carbon. Then we have carbon single bond carbon. So you can see that as the bond energy is decreasing, the bond enthalpy is increasing, right? Okay, moving on further. Then we comes the calorimeter. So it is an instrument which is used to calculate the heat exchange or absorbed during a chemical or physical process. Okay, clear? Now Q is equals to Cm delta T, where Q is what? Where Q is the heat, M is the mass, C is the molar heat capacity constant pressure, and delta T is the temperature change. Clear? Now if M is the mass of substance and C8 is specific heat and Cs is a heat capacity, then how we'll calculate? So for endothermic reaction, Q is always positive and exothermic Q is always negative. So we know it very well. Endothermic because heat is being given to the system, and exothermic means heat is given by the system. After that, let us move specifically to constant volume. So when we say that we are doing the calorimeter calculation at constant volume, then we call it as bomb calorimeter, and that instrument is called as bomb calorimeter. Now origination of the small ignition of the small electrically, there is also evolution of heat which can be calculated. We have seen this. Now heat of loss of summation of the sample and heat equal to heat gained by the water will be same. Why it will same? Because the energy that is produced by the water is gained by the system. Clear? Next we have quantity of combustion of heat. Okay, so if you are combusting something, then the heat of combustion is given as Q of water plus Q of bomb with a negative sign. So this is the overall heat of combustion. Some is taken by the bomb and some is taken by the water. Now, if you use the formula, that is mc delta T, you can easily use it to calculate what? To calculate the Q combustion. So Q combustion is equals to delta U combustion. Okay, we know that delta U combustion equal to Q combustion, and delta H is equal to delta. And second thing, that combustion we have created the volume. So second thing is delta H combustion is delta U plus delta Ng RT. Okay. Now the calorific value of food is what? The calorific value of a fuel is the amount of heat in calories or joule per or per joule produced on the combustion of 1 gram of a substance. So when you do that, the heat that is evolved is called as the what? Is called as the heat in calories is called as the calorific value of a fuel. So more is the calorific value, more efficient the fuel is, or more good the fuel is. So it is given by this, which is change in amount of heat divided by the mass of a substance. Simple. Clear? Now let us try to sum up with a summary. So if you want to write the enthalpy of a reaction, then you can write enthalpy of the product minus reactants. And if you want to write the enthalpy of formation, then you can write in terms of enthalpy of formation of product minus enthalpy of formation of reactant. Then we have enthalpy of combustion, which is basically the combustion of 1 mole of a given substance under the presence of oxygen to a given. So it is basically combustion of a 1 mole of substance to give the corresponding products. Okay, so in case of hydrocarbon, it is carbon dioxide and water. Next is enthalpy of neutralization. So it is basically the neutralization of 1 gram equivalent of acid by 1 gram equivalent of base. After that, we have standard enthalpy of atomization, in which we what we do is the change on breaking 1 mole of a bond completely to do atom in the gas phase. So what we do, we break 1 mole of a bond and we convert it equivalently to gas phase. Then the enthalpy related to that is called standard enthalpy of atomization. We have seen this. Lattice enthalpy is when gaseous molecule come together to form the lattice, and hydration is simply addition of water. Clear? Next is enthalpy of solution, which is lattice minus hydration. So why we've taken lattice minus hydration? Because if you want to break the lattice, then your total energy, that is the energy due to the dissolution and energy due to the hydration, must be same, and they can be used to calculate the delta H lattice. Clear? Now what is standard enthalpy of hydrogenation? So we have seen that. So it is basically the conversion of 1 mole. What is hydration? So we have conversion of 1 mole of unsaturated compound into saturated one, like ethene or butene. After that, you have dilution. We have seen that. So if you are dilating a substance so that no heat is involved further, then it is called standard enthalpy of dilution. And transition is conversion of one electrophilic form to another. Clear? And this can be enthalpy of fusion can be written as delta H naught fusion is equals to minus delta H naught solid, because both are opposite forces, but the heat that is being absorbed is same. Now standard enthalpy of formation is can be written as vaporization can be written as negative of condensation, because again condensation and vaporization are just opposite of each other. फिर we have standard enthalpy of sublimination, so it is conversion of the solid substance directly into the gaseous. Now it is hypothetically done in two ways. First, it is converted to the fusion, which is the liquid state, and then it is converted into the gaseous state using delta H vaporization P. Okay. After that, we have enthalpy of ionization. It is basically the conversion of 1 mole of a substance to to its ions. Okay, conversion of 1 mole of substance to its ions, and to get the products in the solution. Now Hess's law of constant summation is basically a direct application of what? A direct application of that the enthalpy changes state functions. If you calculate it for two states, initial and the final, they can easily calculate the heat of combustion, and this value is always constant. Clear? So it is written in this way. So suppose the reaction is going in 3 parts, 1, 2 and 3, we can write as delta H equal delta H1 plus delta H2 plus delta H3. Now RE is what? Experimental value of formation minus calculated value of formation. Next we have bond enthalpy. So bond enthalpy is next. We have bond enthalpy, Next we have bond enthalpy. Bond enthalpy can be written as a what? It can be written as the sum of bond energies of reactant minus the sum of bond energies of the product. So first we have written reactant and then product. So remember this equation. This is very, very important. Then we have factors affecting the bond enthalpy, which is size, electronegativity, bond length, and number of bonding electron. At last, we have calorimeter, a device that is used to calculate the enthalpy of a given reaction. So this was for today's session, theory session. Thank you.